This I2C is also used for serial data communication. So for example, this is also useful for serial data communication, and it's helping to transfer the data between two ICs within the motherboard. So for example, let's say this is the motherboard of your washing machine in your home. So the microcontroller is sitting somewhere. Maybe whatever the microcontroller, it's depending upon your company brand. Maybe for example, I use Bosch. So in the washing machine, it has a microcontroller and it has several auxiliary chips. So for example, I have the memory chips here, memory 1, and I have memory 2. I have maybe external ADC chip, analog to digital converter chip, or maybe I also have an external timer IC, or maybe I have another PWM IC, pulse width modulation IC. So there will be so many components in the single motherboard. Microcontroller is just one of the several components. So I need to make the data transfer between these chips within this motherboard. This is the motherboard. In the laptop, computer, phone, everywhere we have the motherboard. That is the the motherboard is containing all the components, and there are some other passive and active components, but that's not important here. So these are the important chips, ICs, integrated circuits. So that is integrated circuits. Each one is the integrated circuit. It has millions of transistors inside. So we need to transfer the data. We had seen so far, how can we transfer the data within the microcontroller? The previous slides. So within the microcontroller, you can transfer the data from ADC to internal memory. You can use the DMA mode and so on. But here we have the ICs which are outside the microcontroller, but still we have to have the data communication, the data exchange between this microcontroller and, for example, this memory. So for that purpose, we are using this I2C port. I2C port or I2C peripheral we have in the microcontroller. So I2C consists of 2 wires. SPI consists of 4 wires, but here I2C consists of only 2 wires. So there are which are SCL and SDA. SCL means that is the serial clock line, and SDA is serial data line. So we call this SDA instead of SDL. We can also call this as a SDL. So serial clock and serial data line. So this is for the clock signal synchronization, and this is for data transfer. And the SCL is providing clock to synchronize the data communication. And here, for example, this is one IC and this is another IC within the motherboard. This is a master and this is a slave. It has only 2 wires. One is the clock wire, that is for synchronization, and another one is for data transfer, SDA, serial data line. Okay, so this is for the data transfer. So here you can see only one can transfer the data at a time. So for example, I transfer the data from master to slave. Slave should wait. After receiving the data, then only this slave can transfer the data to master. So SDA helps data exchange between ICs. Yes, this is IC1 and this is IC2. Integrated circuit 1 and integrated circuit 2. Maybe this is we had seen so many example ICs, right? Where is it? Oh, here. So we have, for example, the PWM IC. This is a pulse width modulation IC. And this is the actual microcontroller, your L476. So that is why we call this the integrated circuit. These are integrated circuits and it's inside the motherboard. So there is integrated circuit serial data communication. So SDA helps data exchange between the ICs. Since I2C uses only one wire for data transfer, it is half duplex mode, that you know that full duplex and half duplex, the difference. And both ICs can transfer data, but not at the same time. This is the simple definition for half duplex. Okay, so in SPI, we know only one master and multiple slaves. But here in I2C, we have multiple masters and multiple slaves. So more than one master and more than one slave are possible. So you can connect them in these wires. Just we are using this SCL and SDA as a bus. So this SCL is for the clock and this is for the data transfer. And all are connected to this single cable. So do you remember this is which kind of topology? This is called bus topology, right? This is a common bus. We have the SCL and SDA common bus and all these masters. Here we have the two masters and here we have three slaves which are connected to this bus. But in the slave SPI, we had seen like a circular mode in the ring topology. Okay, so these all the master and slaves are connected to these buses, SCL and SDA, because each one has two wires. And we also have this VDD, and through this pull-up resistor, we are connecting these SCL and SDA to the VDD. That is, maybe if you use the plus 5 volt, then this is the plus 5 volt VDD. And these pull-up resistors, in case if it goes into the floating mode, too much heavy load, then this will bring this SCL to logic high instead of floating mode. Okay, so this is the specialty of this I2C. I2C has more than one master and more than one slave. So we call this as a multi-master, multi-slave mode. So I2C follows the following communication protocol. Of course, in each data transmission must follow certain protocol, communication protocol. Here we define all the rules. So for example, we talk about the write operation. So this is the data frame format. So you can see here MSB and LSB. This is for the slave address. So you should know which slave you are going to transfer the data, in which address you are going to store the data. So this is the slave address, and you have to tell is a read operation or write operation. So from this particular slave, for example, this is the slave registers A0 to A6. So you are going to write the data into this slave address. So what data you are going to write? And you have to also have this A and A bar. The A and A bar is indicating acknowledgement, no acknowledgement. And this is the actual data. So this is the D0 to D7. That is the actual data that is going to be returned into this address. Because after you write the data, if you want to read, you don't know where to read, right? That is why we have the address. So wherever you write this data into, you will read the same data from the same address. Okay, so these are the data byte acknowledgement, and you can this is yes is indicating start condition, and the P is indicating stop condition or start bit, stop bit, and the RW is indicating read operation or write operation, and the A and A bar is indicating acknowledgement or no acknowledgement. So this is just opposite, SDA high, SDA low. So the opposite here is indicating this acknowledgement. This orange color is indicating this from master to slave, and green is indicating slave to master. So you can only do one at a time, not both at the same time, because this is a half duplex mode. So for example, this is the slave address, and you are going to write this data. This is the character A, and this is the acknowledgement if the data transfer if the data transfer was happened successfully or not. So this is just like this I2C communication protocol, and this is for the read operation. This is for the write operation. Now we are seeing the read operation. Everything is the same. And this is the data frame. We have the start bit and stop bit. And we have the acknowledgement. This one is indicating no acknowledgement. It's not received. The data was not received successfully. And R is indicating the read operation. And this is the acknowledgement. And then this is the data, actual data. So this is, everything else is the same. So this is how the data transfer is occurring between two different ICs within the motherboard. The otherwise we can say microcontroller is communicating with other chips outside of the microcontroller using this communication interface, I2C, or inter-integrated circuit interface. So I2C follows the following communication protocol. Yes, this is the SDA, and then this is for the data, serial data line, and this is the serial clock line. So you can decide either you want to transfer the data in the rising edge or falling edge, or rising or falling edge. So you can define that in the microcontroller, the cube IDE interface. So now you can see. So now what I did here is like I enable this I2C. So we have I2C1 and I2C2. We have two possibilities. This is the F103 microcontroller. So we have two I2C, and I am using this I2C2 port. I am checking the sys and the RCC, and everything's okay. I just go to this inter-integrated circuit mode, and then here you can keep it in the I2C mode. So once you do this I2C mode, then these two pins will be enabled. Two wires will be enabled in this microcontroller. One is for the clock and one is for the data transfer. So for example, here we have PB10 and PB11. So PB10 is for the clock, and then the PB11 is for data transfer. And this one pin I am setting GPIO to check the output, and everything else is the same. And you go to the configuration tab, and now you go to the GPIO. In the GPIO, you have this PB8 that you had set up for the LED. For example, the green LED I have set up, and it's in the push-pull mode, not in the open drain. And this is in the input mode and the push-pull. And you can go to the I2C2 because the I2C2 is the one we enabled. So the clock speed, that is the maximum clock speed, we can keep it. And the DMA settings, so we have the channel 4 and 5. So channel 4 is for memory to peripheral, and channel 5 is for peripheral to memory. And you generate the C code, and then you can explore this C code. And this one also is given very clearly in the link I had given. This is actually part of your assignment 3. So it's a synchronous serial data communication. It's used to transfer the data between two ICs in the motherboard, and it has two wires. So that is called SCL and SDA, serial clock line and serial data line. SCL is providing clock to synchronize the data communication. SDA helps the data exchange between the ICs. Okay, so what I wanted to tell you here is I mentioned about this I2C is helping to transfer the data between two ICs. So for example, in this example, I used F103 as a master, this is a slave, and F407 as the master. So these two are microcontrollers. It's not the PWM ICs. So this is a master IC and this is a slave IC. So you can also transfer the data from here to this microcontroller, from here to here. So of course, there are so many examples that you can perform. But in your assignment 3, you are going to use, instead of this one, you are going to use the L476. So you are going to transfer the data between EEPROM and L476. In this example, I am making the data transfer between F103 and F407. This EEPROM is another chip, my integrated circuit. So here you can see. So here I'm using the same I2C2, I2C2. This is for F103. And once you enable that, then you can see here 2 pins that is enabled, 2 wires for the serial data communication with the external IC. So one is for the synchronization and one is for the data transfer, SCL and SDA. And 1 pin to check the output. So now you go to the configuration and then you go to this ADC1. The ADC1, you can set up whatever the mode you want and go to the I2C. The I2C also you can set up everything else. It's in the default mode now. So speed mode is the standard and then the clock speed is the maximum. It's okay. And then you can generate the C code. So this is for F103. So F103 and F407. Whatever you had done so far for the F103, the same thing you have to do for F407 also. The F407 also you have to enable the I2C port, and then immediately the pins will be enabled, and then you can set up the output LED, which you can see the indication how it works. So here you can see in this F407, I am using this sys and everything is okay. So in the F407, you can see how many I2C interfaces. We have the I2C 1, 2, 3, and then the I2C, I2S 2, 3. So we have several possibilities. So that is why whenever you go with the high configuration of microcontroller, little bit expensive one, then you have more interfaces, more peripherals than the cheapest one. So here you have so many, and then we are using only I2C 1, and then we can go to this I2C and then do the configuration. So the configuration is the same, and then you click OK, and then you generate the C code. So everything else is the same for this microcontroller. Yeah, so you can find this hardware in the lab, and then you can start your assignment 3 and 2 and 3.